APN6 is a new technology that enables networks to be aware of applications, but the concept of application-aware networking is not new. While decoupling networks from applications has always been a controversial topic in the industry, the requirement for networks to be aware of applications becomes increasingly high as new applications continue to emerge in the 5G and cloud era. How to meet this requirement is now a hot research topic. A traditional network cannot be aware of applications or their requirements. This means it can only provide non-differentiated services. For example, it provides the same bandwidth service for all applications, regardless of whether they require high or low bandwidth. It also needs to provide high bandwidth even when traffic is light, so that it can avoid packet congestion or loss when traffic is heavy, which is not cost-effective. With a technology that enables it to perceive applications, the network transforms from a common pipe to an intelligent pipe. It can then provide differentiated services for different applications. IPv6-based APN6 is such a technology. It can convey application attributes to networks. An application-aware networking technology integrates both identification technology and a marking technology. The former is used to identify the application group to which a packet belongs, and the latter is used to mark the service requirements of the application group. The two work together to provide differentiated services for different applications. Traditionally, the mainstream application identification technologies include 5-tuple and DPI. 5-tuple application is based on flow information and can only deduce applications indirectly, resulting in low identification accuracy. Once the 5-tuple of application flow changes, manually adjustment is required, making O&M more complex. DPI is short for Deep Packet Inspection. This identification technology can accurately identify applications based on packet characteristics to some extent. However, it has high requirements on network devices and needs to be implemented on each node, severely reducing the forwarding efficiency of the entire network. Now, let's discuss application marking technologies. Traditionally, traffic is classified based on queue's priority field, so that a network can provide differentiated services of different levels. This approach cannot accurately mark the service requirements of traffic in detail, and only classify packets into a limited number of categories. As such, it cannot meet requirements when there are millions of applications. APN6 provides two optional solutions. You can choose one based on your network evolution status. The first is a network-side solution. In such a solution, after receiving a packet, a network edge device identifies the application group and marks its service requirements in detail, including the specific values of bandwidth, delay, jitter, and packet loss rate. Subsequent nodes can then provide on-demand service guarantee for the application group. The second is an application-side solution. In such a solution, an application itself determines whether to generate an APN ID. After receiving a packet that carries an APN ID, a network node learns the application group to which the packet belongs based on the APN ID, without classifying the packet or performing DPI on it. Such a solution is more accurate and refined compared with the first one. From this detailed comparison, we can see that APN6 integrates both application identification and the marking technologies in order to be aware of applications in a more refined manner and express service requirements more accurately. It can also convey APN IDs across the entire network after identifying them on a single node. A network needs to be aware of applications so that it can provide services that these applications require. Now, let's see how APN6 works with other technologies to guarantee service performance for important e-government video conferences. If APN6 is deployed on the IPv6 SRv6 e-government network, the video terminal adds APN IDs into packets for important video conference traffic to convey them to the network. The network head-end maps the traffic to SRv6 passes that meet SLA requirements based on the APN IDs, accurately assuring performance for applications. If IFIT is also deployed on the network, APN6 can work with IFIT to implement refined in-band performance measurement for important video conference traffic in real time, achieving full process performance visualization. Once the SDN controller learns that performance has deteriorated through IFIT, the controller selects a suitable backup SRv6 path and quickly switches the traffic of important video conferences to this path, implementing real-time monitoring of network performance for applications. So, we can see that APN6 can work with SRv6, IFIT, and the SDN controller to guarantee the network quality for important video conferences. APN6 can also work with other IPv6-ready network functions such as network slicing, SFC, and SD-WAN to provide refined and abundant network services for applications. To sum up, APN6 serves as a bridge between a network and applications, and is the most suitable application-aware technology for enabling an intelligent network pipe.